one is AI using, hmm, yeah, my research topic is AI using Spintronic and other emerging devices from device to system. I was at IIT Delhi from 2017 to 2020, 2017 to 2020, 21, and then I just recently moved to IIT. I recently moved to IIT Bombay. So, in terms of my research work, I basically what I try to do is this is AI. My like main the major motivation for this work is AI, but then again at the same time it's not like the conventional AI where you about modifications to this AI algorithm so that they can be run more efficiently. And so for that, we need to come up with new devices, new hardware, and we need to come up with, yeah, so we need to come up with new devices, new hardware, and we need to come up with new architectures so that this AI can be implemented in this novel hardware for low energy applications. And what low energy applications? Typically in wireless sensor networks or in case of robotics applications, you are often computing at the edge. You're computing, but you are detecting your signals from your sensors. The inputs are coming in from the environment, and you're trying to do some amount of control, do some kind of learning activity or some intelligent activity there. So there, unlike running it an algorithm on a major on a big computer, on the compared to that at the edge at this sensor nodes, energy becomes an important bottleneck. Okay, speed becomes an important bottleneck too. So if we can come up with more innovations in terms of the architecture, in terms of the algorithm, in terms of the devices, then the AI can be more feasible to implement it at the edge. So that is the main motivation behind my research. So what I will do now is we will start with I will discuss what are the kind of devices that we work on and what are the kind of systems that we work on. So mainly my work is on spintronic devices. So my first part of the talk will be about spintronics for not AI but regular computing. So through that you will get a flavor of what spintronics is and what nanomagnets do. Then the second part is spintronic synapse for in-memory computing or hardware AI, which is basically edge AI, which is what I work on. And the last is transistors, conventional transistors for doing similar kind of edge AI. And so that is from a device perspective, but then I don't work just on the devices, but I rather work devices as well as on circuits and systems. So from a circuit or systems perspective, the major sub projects that I'm going to cover are in-memory computing with spintronic transistor synapses. So the devices that we talked about, like in number 2 and number 3 here, how to make a crossbar array of those devices to do in-memory computing or neuromorphic computing, and then how to, instead of using non-spiking behavior, if you try to take inspiration from the brain, and you're looking at spiking patterns and you're trying to reproduce those spiking patterns on your network, what kind of modifications do you make to the crossbar? Then apart from that, another computing kind of which is of our interest is computing using oscillators, because oscillators can act like neurons, like just like neurons in brain have been found to be fairly oscillatory. Oscillators can, the SH spin Hall oscillators, the spintronic oscillators are also fairly they exhibit auto oscillations, and then they can synchronize with each other like neurons in the brain can. So we also explored how you can do computing with this kind of oscillator arrays. And the last one is quantum computing, how to use quantum computing for AI purposes. So these are the four major so within devices perspective, I think I can categorize my work into three parts. And then from a systems perspective, I can categorize my work into four parts with major overlap between these different parts. All right. So with that, if somebody wants to, so I think the best way to go is I just stop here and there, like after covering a few slides, I just stop. When I cover a particular concept, then I open up the forum for questions. So I think before I move forward, if people have questions at this point about the scope of the talk, that will be pretty good. Mhm. Any question thus far? Please feel free to ask questions. Hello? No questions? Okay, so let me start with the devices. So from a motivation from a device perspective, what is the major motivation? Now we know that at a processor, okay, like the microprocessor that is dominate the computing industry today are made of transistors, metal oxide semiconductor field effect transistors, right? And this is basically a three-terminal device where you have source and drain, and the source and drain are connected by a by a channel. And the channel is typically induced in the semiconductor by applying a certain voltage at the gate. So far, so good. All right. Now, if I look at these transistors or how transistors are scaled, you see that earlier we used to have a much larger size computers with much lower efficiency, but now we have much smaller computers, very small microchips, which have a lot of efficiency. And the reason for that is because the transistor size has gone down over time. So as the transistor size has gone down with time, the transistor density has also gone up, and that has led to more functionality, higher speed, etc. Scaling has lots of advantages. But then there are downsides to scaling as well. So what happens typically is that when you have a long channel MOSFET, your switching is very sharp. That is, you can switch very easily from off to on and on to off. On the other hand, in short channel, the switching becomes more gradual. You can see the slope of the blue curve is much higher than the slope of the red curve. That means the switching is more gradual in the blue curve, in the red curve as opposed to the blue curve, and the red curve corresponds to the short channel MOSFET, right? And now, apart from that, the threshold voltage which you're looking at, as you're scaling down in technology, as you're going shrinking the dimensions, the threshold voltage goes down. So that means this curve moves further towards the left. And so if this curve moves further to the left and the slope goes down, what that typically means that at gate voltage 0, we have a significantly high off current. So high off current is a major issue with spintronic devices. That is, if this off current is high, we are not being really able to switch the transistors off. And that is why what has happened is as the technologies have scaled, the operating voltage we could not reduce further and further, because reducing the operating voltage further and further would mean reducing the threshold voltage further and further, which would mean increasing the off current. So and that comes at a cost. If you do that, what happens is when as you've shrunk the transistors in the earlier generations, as we shrunk the transistors, the clock frequency could be increased. You could make the processors faster and faster. But now, as you make the transistor dimensions shrink, now you cannot make it that fast anymore, right? So which basically means the clock frequency, the frequency is saturated and power density, and this is, and because of this only the power density has, we have not been we have not somehow been able to stop the power density from rising to alarming levels. Okay, so power density is also kind of saturated. But then if you're trying to implement electronics with this, the edge, where your energy is a constraint, but your battery life is a constraint, then this becomes a problem, because that you are consuming a lot of energy and a lot of power in doing it. So as a result, here spintronic devices can be useful because the magnets are very efficient switches and they consume very low power while switching. Okay, so that had led me to explore the physics of some ferromagnetic devices where you have these magnetic materials like cobalt and boron, which is like 1 nanometer thick, sitting on the top of like a tantalum bar or something, which is like about 10 nanometers thick. This is a heavy metal. So when current flows through this heavy metal, you essentially generate a lot of spin polarized electrons in heavy metal, and the spin polarized electrons are so efficient that they can switch the magnet. Now we showed that if you have, we measure, and these measurements were done on about 200 nanometer size magnets and all, and then we show that in this kind of structures, if we apply current and then we measure voltage on the other side, we measure a nice anomalous Hall effect. Anomalous Hall effect, one resistance, the lower resistance proportional to magnet down, the higher resistance is proportional to the magnet up. And you can actually apply magnetic field to switch between up and down. But interestingly, if you apply a large amount of current, you can generate a spin out bit top, because of which this magnet starts behaving like a coin, which, between head and tail, right? So it is flipping between head and tail pretty with about a 50% ratio, and you can essentially do that. But then if you bias the system, what happens is this current that which was making it head or tail, based on the dipole field, you can bias that system to switch in a particular direction. And once you do that, you can implement some complementary logic with it, like NAND gate or NOR gate, which are very power efficient alternatives to the standard CMOS-based NAND gate or NOR gates that you see. So here we have an experimental demonstration that all the magnets are vertically up. Now, when you apply a certain current, the magnets are driven to a metastable state, and then the magnet goes down. The next is up, the next is down. All right. So the dipole, what happens is the passing of the current makes the system like a unbiased coin, and then the application of the magnetic field adds some bias to the system, and it leads to specific directions of the moments up or down with which you can do computing. And we showed like nanodots, like about 200 nanometer size magnets, which is separated by like 30 nanometer. And then you apply a current. Yeah. And then when you apply a current, some magnets are switching up, some magnets switching down, following this order. You start from all up, and then you have this one up, then next down, next up, next down. So it's like a chain of inverters, and which you have been able to clock or apply current by applying this spin orbit torque. And it has been shown to be very efficient when compared to magnetic field, and that's why this work was published in Nature Nanotech back in 2014. So this is like the early part of the talk where I'm not talking about AI yet. This is Spintronics for doing computing work. All right. Any question at this point?
So,
Mm-hmm.
so exactly like to the device, what is the input that we are providing? Like some voltage, we in MOSFET we apply some voltage. So in this we are applying some magnetic field, or it's
No. You are not applying a magnetic field because a magnetic field application is very inefficient, right? So if you apply a magnetic field, how can you really make a circuit with it, or how can you do like a practical processor with it, right? You cannot really apply fields to the system. What you do is you apply current, and this current this heavy metal, and the current generates spin polarized electrons. So we are playing with there are quantum mechanical phenomena happening at this interface, which we are exploiting. All right. So when you pass current through this material, you generate electrons with spins in a specific direction, and these electrons interact with the magnet and they transfer angular momentum to it. And these things happen within a nanoscale. It cannot happen beyond like 1 or 2 nanometers. All right.
yes, sir. Thank you.
Any other question? Any other question? Hello? Hello? No? Okay. So let's move ahead. Yeah, let's move ahead. Now we take a, now the question is, we earlier showed that on a smaller magnet, if you apply a current pulse, it's switches to it is either up or down. Now, if what happens to a larger magnet? So when you apply a larger magnet, what happens is typically this magnet is not completely up or completely down when you apply a current. Rather, it goes to a mixed state, that is some of the moments are up and some of the moments are down. And the region which separates this all down polarized moments from the up polarized moments is called the domain one. Okay, so now what you do is when you apply large current, you see this kind of domain one, you see this white dotted line, it is separating this dark image from the gray image. And this is all again your measurements through curve microscopy. And then what you show is that on that, if you apply a current, your domain wall either moves orthogonally downward or orthogonally upward, right? So the domain wall moves orthogonal to the direction of the current, and you can see a complete switching. Okay, so this shows that if you apply current, you can actually control the motion of domain wall, and we have done this experimentally and measured this through magneto-optic imaging. Okay, so now based on this idea that a domain wall is a region which separates moments pointing down from a moment pointing up, and the fact that we can move the domain wall with the current, you can propose an interesting device which is called a synapse device. And to some degree, it copies the synapses that are there in the brain. So a domain wall is what? It is separating a region from moment down from a moment up. So if the domain wall moves, the region with moment down goes up, the region with moment up goes down. Similarly, domain wall moves leftward, the region with moment up goes up, the region with moment down, it shrinks in size. All right. So a motion of the domain wall corresponds to the net magnetic configuration, the net magnetic moment of this whole thin film in which the domain wall is moving to change. All right. And if you apply a right current pulse, this domain wall moves, and your net magnetic moment contribution, or the net magnetic moment amount is actually changing in this system. Okay. So now I'm given this a magnetic system. If the fact that you can move the domain wall, that means you can have different values of magnetic configurations, and if you can read them out through some kind of tunnel junction structure, that means you can have different values of weights. So we did show through simulations that if you build this kind of device systems, simulate these device systems, and in them you have these domain walls, and you apply the current through it, the domain wall moves leftward for one kind of current, the domain wall moves rightward for the other kind of current, right? And then if I measure the voltage of these devices through tunneling magnetoresistance, and you plot the corresponding conductance, you see the conductance is nicely going up or the conductance is nicely going down. And we'll see later on in the later part of the talk how this conductance going up and going down can be useful for weight adjustment in a synapse and to train a neural network. So if some of you have done some machine learning course, you would have seen that in neural network algorithms, you start with the matrices of weights, and then as you are training the network, the weights get adjusted, the weights get trained. So this synaptic devices can store those weights, and the weights can get trained again and again, all right, to achieve the training. And if I compare this with other competitive devices like resistive RAM and phase-change memory, I see that resistive RAM and phase-change memory have these issues that in one direction it is easy to increase the conductance, like it's easy to increase the conductance in those devices, but reducing the conductance happens, decreasing the conductance, reducing the conductance, lowering the conductance happens by an abrupt jump. So that's why that is a major disadvantage with charge-based non-volatile devices like resistive RAM and phase-change memory. So compared to resistive RAM and phase-change memory, domain-evolved synapse doesn't have this issue, and so the time for learning is much lower, and the energy for learning is also much lower in the networks. Okay, so this paper won the IIIT Advances Mechanism Award back in 2020 because of showing this particular innovation. All right, so now the thing is, that ends my Spintronic synapse for in-memory computing. I will get later on, I'll get into more details with it on how to design these crossbar arrays with these Spintronic devices. So some more questions, please. No questions?
There is one question in the chat.
Yeah, please read it out. Can you please someone?
Okay.
I cannot read it.
Won't the nearby magnets severely affect the performance of such devices?
Say that again.
If there are nearby magnets or magnetic field, can it affect the performance of?
Yeah. So that is one downside of magnetic logic. That is, if there are nearby magnets, then you will be affected by their behavior will be affected. But at the same time, you have to remember that we do have. 1 second. This size is not changing. Yeah. So at the same time, you have to remember that we do have something called magnetic hard drive, which are there in the computers. Nowadays, it's more solid state drive, but earlier there used to be magnetic hard drives, and they were essentially storing magnetic configuration, but they used to work pretty well unless you bring it close to a strong magnet, when all the information will get erased. So the same thing over here with magnetic logic system. Sure, if you bring a large magnetic field, it will be affected, but in the regular course, in the wherever you're working, unless you bring it close to a large electromagnet, the magnetic field is not strong enough to affect your configurations. Make sense?
Yes, sir. Yes, sir.
Okay. Anything else? Okay. So we take a quick break from nanomagnets, and we also look at transistor devices for synapse properties. And why so? Because though these nanomagnets are very promising and they're low energy, take low energy and all, as you know, it's not a very popular thing, and that's why not many people know about it. And this is because it's very hard to fabricate those systems for large purposes. It's okay to fabricate such systems for a simple computing thing, but for fabricating very large systems for a lot of computing application and all is not very straightforward, right? So what happens is what we do is the thing is what we do is we also try to explore simple charge-based devices, charge-based transistor devices, so that we can try to consume the charge-based devices are volatile like a transistor, and so the charge, but if I store the weights there in terms of the charge on the gate, then there is a chance of losing that charge because of the rest of the circuit. At the same time, when you try to do neural network training, I don't need to remember those weights or those intermediate weights forever. I need to remember them for a short period of time. And that's why the question is, can we use volatile devices like transistors to do the computing? And we did show that just like in case of magnets, you apply current and you can change the conductance. Here also, by applying gate voltages on this capacitor, gate oxide capacitor of the MOSFET, and by slowly charging it or slowly discharging it, you can actually modulate the conductance between drain and source. You can think of it as a three-terminal device. Between the gate and the source, you apply a voltage. As you increase the voltage, the conductance of between drain and source goes up. As you apply voltage in the opposite way, the conductance between drain and source goes down, right? And we showed that a very nice linear characteristic. And then if you try to train simple fully connected networks with no hidden layer with it, you actually get a fairly high accuracy, and the runtime is also pretty low. The energy is also pretty low. Now that is again from a device perspective. Now we move to a more systems perspective, and we talk about how at a systems level we can do things with this, right? So, one second. Compared to Teams, this is a bit slow. Just hold on. So yeah, maybe the computer is taking some time to respond. So maybe in that time, if you have any question, you can ask me. So getting a bit slow down. Okay. I'll share again. Can you see the screen?
Yes, yes.
Okay, so I stopped sharing once and I'm sharing again, and now it works. So did any people get the idea that how this transistor device was different from a Spintronic device in terms of acting as a synaptic device? Was the idea clear? People can ask me questions like, what are the main differences between having a Spintronic device for a synapse, like a weight modulation device in a network, and having a transistor device?
No, so can you please repeat this part where it is acting as a, we can learn this weights?
Yeah, so a synapse device is
Linearly.
basically a device which stores many values of weights, and you can go from one weight value to another, right? Or some other weight value to another electrical. Now, when it's a Spintronic device, what happens is you apply current, and this current moves the domain one, and the magnetic configuration changes, and so you have different values of conductance. On the other hand, in case of transistor device, what you do is you apply current pulse on the gate that charges up the gate. You apply some more current pulse that charges up the gate. How? Because you are essentially charging up the capacitor of the gate oxide capacitor. And then as you are charging up this gate, that means your gate to source voltage changes. And we know from basic MOSFET physics that if the gate to source voltage changes for a given drain to source voltage value, you have a higher drain current, right? So your conductance between drain and source, right, which is IDS, the current drain current over the drain to source voltage, that conductance is modulated by modulating the gate to source voltage, which is in turn modulated by applying currents to the gate. So just like in the Spintronic device, a 3-terminal device, where current pulses to the third terminal or the right terminal changes the conductance between the other two terminals, here also current pulses applied at the gate is changing the conductance between the drain and the source. Okay, and this was a device proposed by our research group. And the good thing about this device is much easier to fabricate than a Spintronic device, because this is just a regular MOSFET.
So we are taking our MOSFETs only running in only in the linear region.
Yeah,
so that
exactly.
I can learn the region. Okay.
Yeah, so if you apply the MOSFET in the linear region, you already know that the IDA versus VDS, that follows the linear curve, which we call the linear region. Now in this linear region, ID versus VDS is the slope is a function of the gate voltage, right? If you have a higher gate voltage, you will have a more drain current for the same drain to source voltage, right? Right, so the slope changes. So that slope is your conductance, GDS. And so by changing the gate voltage, you are being able to increase or decrease that conductance. Okay, and that corresponding to the conductance, you have your weight. Okay, just like in case of a Spintronic device, corresponding to the conductance, you had your weight. So now my question to you is, both are 3-terminal devices. In both cases, you're applying right current pulses into the gate and not being able to change the conductance between the other two terminals. But what is the fundamental difference between those two devices, these two devices?
So maybe we can say, like in case of conventional one, we are using charge as the medium of transport, but in the other one, it was the spin electrons, the spin orbit.
So what consequence, that is the mechanism, but what consequence does it have in the device property? Like when it comes to neural network training, and imagine that for every conductance value you have a corresponding weight, what consequence does it have that one is charge based and other is spin based on the device property?
In the charge base, the weight will be the continuous. Otherwise, in the spin base, it is a discrete weight, either 0 or 1.
No, the spin base is not a discrete weight, because it would have been a discrete weight if you had a very small number of spins. But if a fairly large device, you can actually control the number of spins. So if you look at this picture, if the domain, the blue region is where at the moment the spins are all up, and the yellow region is where the spins are, sorry, blue region is where the moments are all down, yellow region is where the moments are all up. Now, as you move the domain wall, the number of moments with down and the number of moments up, they are varying. You are having many possible values between 0 and 1.
So my one question is that if the weights are continuous even in spintronics or in the conventional one, how does process variation affect these weight values?
So that is a deeper question, but I am asking a more fundamental question to you. That is, what is the difference between a spin-based system and a charge-based system when it comes to storage of these weights? Right? If I use a spin-based system as a synapse to contain my weight, or if I have a charge-based synapse to contain my weight, what is the difference?
So just a guess, or does it like we can have a leakage in case of charge and
Exactly.
not much
So
in case
it's the same thing is true between SRAM and your and a magnetic hard drive, right? Or between SRAM and a flash memory, right? SRAM is a leaky system, or a DRAM is a leaky system, right?
Yes. So in case of like magnetism, this won't happen, like leakage problem won't be there.
Right. So everything is coming at a cost. It's easier, it's cheaper to build transistor-based systems across bus, but then you have a leakage problem. On the other hand, in Spintronic, you don't have the leakage problem. So what do you think is the consequence of a leakage problem? You're starting with some random values of weights, and you're gradually trying to train those weights to train a network. So you're modulating the weights till it reaches the appropriate values, right? So what is the consequence of leakage, do you think? If the charge starts leaking from the gate, what happens?
The values
what
that the values that we are storing, they will get altered. Like
yeah. So I think she has the right answer. Corresponding to your conductance, you have your weight, and the conductance is a function of the gate to source voltage, which gate to source voltage depends on how much charge you're having at the gate, right? So if the charge starts leaking, my gate to source voltage changes, so my conductance changes, so my corresponding weight values change. So if my network starts from random values of weights and I'm trying to train it, if it is a very short duration, for a very short duration I am trying to train the network, then this method works. Okay, by the time the charge starts leaking, I am able to train the network. On the other hand, if I am working on a more complicated network like a convolutional network, then this method doesn't really work well. So I'll tell you the story. When I started my work at IIT Delhi, we were always working on Spintronics-based neuromorphic, but we also were very hopeful that this transistor synapse-based neuromorphic or transistor synapse-based crossbars will be very useful because they are cheaper than Spintronics to fabricate. You can easily make it in a commercial fab. And we are very hopeful that this thing is going to work. But then as we published these papers and as we did it over the last few years, so around 2018, 19, 20, we were heavily working on it. And we realized that while this works well for standard fully connected networks, easy fully connected networks for solving easy problems, the moment we go to larger, the bigger problems with convolution network, it doesn't work. Make sense? Because you start losing those weight values, the weight values get altered, as she was saying.
So my question is it not possible like a DRAM that we can refresh these devices and restore the weights? Is it possible like a DRAM that over the time we refresh the DRAM and restore the data stored in the DRAM?
So this is interesting. So this is interesting. And our idea is very similar to the DRAM idea only. Now the thing is, the problem is that if you use a DRAM is typically storing a 1 or a 0. All right.
No.
Right.
Okay.
Each DRAM cell is storing a bit, and refreshing the DRAM is basically retaining that 1 or retaining that 0, isn't it?
Yeah.
Now, if I look at this MOSFET synapse, it was actually trying to store, if we look at the number of conductance values, it was actually trying to store 50 or 60 values. So basically 4 or 5 bits. So 4 or 5 bits were there in this transistor synapse. If it starts losing that value, I cannot really feed it current and bring it to that particular value I want. You get what I'm saying? If it was just storing 1 bit and it was losing it, you can put a current. In DRAM, I don't think you have a controlled current, right? You just refresh it by putting the same amount of current, it just stores it, right? So a DRAM idea will work. So instead of having one synapse, if you have like 5 or 6 transistors, and each of them I'm refreshing it, then this will work. But then there are other groups who are working on it. So you can look up those papers. It's called DRAM cell papers, right? So DRAM based crossbar arrays of neural networks for training neural networks and all that, right? So that will work, but because we are trying to store multiple bits, like 5 or 6 bits in one synapse transistor, this idea doesn't really work well. Makes sense? No, that's a good insight. Okay. So now we have covered the device aspects of things. So let us move into the systems aspect of things. All right. So since you are an interactive group, I would say you can look at this and you can appreciate what are the different places or applications that people typically use of AI, right? How many of this you are aware of? Hello?
Yes, sir. So most of
You're aware of most of them? You know that with AI you can build these computers which can beat human champions at different games like
yes, sir.
chess, Go, etc. All right, and everybody knows our self-driving car and virtual assistant, right? So if that is the case, okay, going to the full screen mode creates problems. Okay, so now if we look at this neural network algorithm, so what is the most popular neural network algorithm that people? What is the most popular AI algorithm that people use at this moment? Hello.
CNN.
Okay. CNN. And what kind of problems do people use CNNs for? For all kinds of AI problems, do people use CNN?
Classification.
Mainly for classification.
Classification of what?
Mostly computer vision problems.
Yeah. So mostly for image kind of problems, people use CNN. When it comes to speech, converting speech to language and all that, written language and all, what do people use?
LSTMs.
LSTM is a kind of recurrent neural network.
Recurrent neural networks. Yes.
So LSTM is a kind of recurrent neural network, isn't it?
Yes.
Yeah.
So
recurrent neural networks is a broader term. So we have not really started working on how to implement recurrent neural networks with Spintronic devices. We have mainly worked on how to work with implement fully connected network and convolution network with Spintronic devices, right? If you look at these networks, at least, what is it? You are doing supervised learning. So you have a set of weights. Okay. Hello.
Yes, sir.
You have a set of weights and you are trying to modulate these weights, isn't it? Right? And what you do is you have your weight matrix, you multiply to the input, then you apply some nonlinear activation function, again multiply some weights, again apply a nonlinear function. Then you try to compare your output with some desired output, you calculate the error, based on the error you update the weight, and you keep doing this over many iterations till your error minimizes, right? Okay. All right.
Yes, yes.
But then why is it just an error minimization problem? As in, is it just like I've been given a lot of training data, a lot of inputs, a lot of outputs, and then I'm trying to minimize the error and fit the curve? Is it just that? Is training a neural network just about fitting a curve? I mean, if you fit the curve really well on a training data, is it a good thing?
It has to generalize. So if we fit it really good, then there might be overfitting problems. And
right. So what is exactly overfitting? Can you explain?
Yeah, it will work very well on the training data because it has actually learned what the training data is, but it won't generalize to the test data, the one that we have not yet feed it. So it needs to generalize to that also.
Makes sense, right? So basically your job is not just that I've given you 1,000 images and told you this is cat, this dog, this is plane, this is this and that. You just, on those images, you can make your inferences. It's also about if you get new data, can you really do your job or not, isn't it? Right?
Yes, sir.
Okay, so that's why the training, along with training accuracy, test accuracy becomes a very validation accuracy, and test accuracy becomes very important parameters, right?
Yes, sir.
Okay. So now if I look at conventional implementations of these neural network algorithms, what do you typically do? You have your, so you understand the von Neumann architecture, right? Which all computers follow, right? At least the standard conventional computers, you have heard of it?
Yes, sir.
So what is von Neumann architecture? Is shown in the figure. What is the definition? Like what is exactly von Neumann architecture?
where
like
the
the memory
compute,
is
the storage
So
unit, both are
memory and compute units are essentially separate entities, and
that is what you see in this.
data
That is
for
what,
computation has to move to and fro.
and that is what you are seeing in this picture, right? Aren't you?
yes,
Right.
sir.
So
Yes.
now in the memory you have these multiple hierarchies. You have this one hierarchy of memory, but you have these multiple kind of devices at these various stages. You have cache. You have cache is the part of the memory which is with the processor. Then you have the main memory which is away from the processor. And then you have the storage, right? As Spintronic devices, people have thought of using or everywhere. For storage, it is already being commercially used in magnetic hard drives. For memory, there is this STM RAM, which some of you may have heard about, or SOTM RAM. So these are people thinking of using them for memory as well as for cache. Okay, and in the other hand, for processor, I showed this magnetic logic where people have thought about using it for processor, but then it is not very fast and it has all these issues. So now when we try to think of neuromorphic computing or in-memory computing or crossbar computing, we essentially challenge this hierarchy, right? What we do is so we try to challenge this hierarchy in different ways, right? So we do is we say have a crossbar array of networks or a crossbar array of devices. Now in this what I already told you that you essentially need to do a lot of matrix vector multiplication in the case of running neural network algorithms. Now if you think of it, if these devices, the conductance of these devices are proportional to the weights, as I showed you before, then if you apply voltages which are proportional to these inputs on this horizontal bars, then the current flowing through these devices, they will add up following Kirchhoff's current law, and you will essentially have your input matrix multiplication. Is that clear? That's very important for the rest of the talk. Understanding how this crossbar relates to the input vector multiplication shown here. This WX multiplication that we're seeing, this weight is the synaptic weight matrix and X is the input. So you apply your X at the signals here and your matrices correspond to your W. Is that clear? Hello?
Yes, sir.
Yes, sir.
That's clear. So what is the advantage of doing it this way compared to doing it on a regular one-hour architecture? What do you think?
So we save lots of energy latency.
Yeah, the latency issue you are going to be able to work out a bit, because here you are constantly doing what? You're taking these weights, fetching these weights from the memory, bringing it to the processor, doing the computing, putting it back in the memory. Again, fetching the weight from the memory, doing in the computing, and then fetching it back in the memory, right? So this continuously back and forth of weight values, right? The back and forth between these weight values, that it consumes a lot of energy, that it consumes a lot of time. So you can do away with it if you are using these crossbars, because your computing is happening in this crossbar and the update of the weight is happening in this device itself by tuning the conductances. Make sense? Does it make sense?
Yes, sir.
Okay. Now let's go into more details about it. Right? Another thing is there the multiplication is not parallelized. Here the multiplication is parallelized. So all these individual multiplications of these different matrix elements with the inputs, they're happening all at the same time. So what is the complexity of this? If you look at time complexity of this process, right? If I multiply an n cross n matrix with a vector, input vector of row n, right? And each scalar multiplication is your fundamental step. Then what is the time complexity of that? Right? If I do a wx multiplication here, w is n cross n and x is n, right? And each scalar multiplication, not vector multiplication, scalar multiplication is your fundamental unit. Then what is the complexity?
And
N or n square? Should be n square, no?
yes, sir. It should be
N square, right? If you are doing one scalar multiplied by one scalar is your fundamental unit, and how many multiplications, such multiplications do you need? N square, right? So if your fundamental unit is multiplying one scalar with one input, then you need n square operations. Of course, with GPUs and all, you can make it faster. You can do like a vector with a vector kind of thing, make it probably ON or something. But here you are essentially making it O1, right? All of these are happening at the same time, isn't it? Yes.
Yes, yes, sir.
Yes, yeah, here the complexity is very.
Any doubt?
No, sir.
Okay. So now you see that the weights multiplied by the input, then you apply a nonlinear activation function, then you calculate the error, and then based on the error, you fit the you feed you based on the error, you feed the weight changes to the synaptic matrices and the weight values update, right? So what we do is we model this domain-wise synapses on micromagnetics, and we get this conductance versus current pulse property that we had shown you before. Now we convert that into some kind of Verilog A model, and we place this Verilog A models in your SPICE simulator, right? And then on Cadence Virtuoso, and then on the SPICE simulator we run this simulation. Okay.
Yeah, sure.
All right. Now on the SPICE simulator we run this simulation, and you are applying the inputs at your horizontal bars, and you are applying the outputs at your vertical bars, isn't it?
Sure.
Sure.
Yeah.
Okay.
Yes, sir.
Okay. So what now on those outputs, what we do is we design peripheral circuits, analog peripheral circuits, which act like neurons. Make sense? And these neurons are applying a nonlinear activation functions, and you can design these neurons with different analog designs and all that, right? Like for example, for having a 10H neuron activation function, you can have an op-amp set of op-amps like this. Like some people try to do these activation functions with magnets as well, and that's also doable. It's just that it's complicated and it doesn't really serve much of a purpose because neurons do not need to be non-volatile. So why use magnets when you can do it transistors? So my design principle is use magnets only when you need to. If you don't, use transistors. Okay, if you don't want to, then use transistors, right? Now the common part of to calculate the common part of the weight update, and then we calculate the update those weights. So and then what we typically do is when we are trying to do this kind of designs, we need to have some quantizers as well, because these quantizers enable the weight update. So earlier I was saying that the weight update at the synapse is basically input multiplied by common part of weight update. And if you want to do it with those devices, right, on those devices, then I need a very complicated multiplier with the synapse device. To avoid that, we try to do some thresholding, and so we use some transistors so that we can do that multiplication with just 2 transistors. Now this is a lot of detail and I would not expect you to learn it right away, but you get the big picture that we essentially build this kind of crossbars, and we are able to update the weights of these elements, and we're able to train the network. And we show these things on circuit simulations on Cadence Virtuoso. All right. Now, how many of you are aware of the backpropagation algorithm?
Yes, sir.
Okay. Now, in the backpropagation algorithm, you have multiple layers, right? Now, the weight update in the last layer, does it depend upon the weights of the previous layers? The last layer. I'm starting my input, then I have this layer, then I have another layer, all the way to the output layer. The weight update of the last layer, the penultimate connecting with the final. So those weight updates, do they depend on the previous layers?
No, sir.
No. But if I look at if I go for the left on this, like for example, the weight update of the first layer with the second layer, do they depend upon the weights of the previous layers, of the other layers?
Yes.
Right. So the input during forward computation, the signal is going like this. In the reverse, in the weight update time of the weight update, the signal is going back like this, isn't it?
Yes, sir. Backpropagates.
Backpropagates, right? So when you do this backpropagation in your computer, all you do is write corresponding equations, and you have a physical intuition for the backpropagation, but you're not really backpropagating signals, right? When you train a fully contained network on a Python code, are you really backpropagating electrical signals? No, right?
No, sir.
But here we are going to really backpropagate electrical signals. See? So what happens is this crossbar 1 is input layer with the hidden layer. Crossbar 2 is hidden layer with the output layer. Then based on the weight update calculated in the output layer, we know that the weight update of the first layer depends upon the weight update of the final layer multiplied, if you have 2 layers, first of all. So weight update of the final layer multiplied with the synaptic weights of the other layer, right? So we do that. So that multiplication is happening in this extra crossbar and it's coming in and then you're updating these weights. Make sense? Make sense?
Sure.
Okay. Hello? Hello? Okay. So now with that, we see that if you don't have the hidden layer, then the accuracy is pretty low. But when we have the hidden layer, the accuracy goes much, much higher. All right. And that is, I think you already know that what is the advantage of having hidden layers, right? So why do hidden layers improve the accuracies? In ML, in neural networks, huh?
It's able to learn more abstract features.
Right. Because of these nonlinear activation functions that you have, right?
Yes, sir.
So good. So we already, so what I'm trying to say is by being able to make this kind of design, we make it possible that we can train these multi-layer networks in hardware as well, right? And that is good. So we have better accuracy because of that reason. Make sense?
Yes.
Okay. So now I showed you this work with my Spintronic devices. Now we were curious, right? That what happens when you have transistor synapses instead? Were you curious or you not? Right? That because transistor devices are easier to fabricate, but they lose the weight. So what happens with that? So we do see that with those transistor devices, if we do some intelligent design, again, the multiplications become challenging because at every stage, you have to multiply the common part of the weight update with the input to cause the final weight update. So we just do this kind of digital cells to do that. And then we here the additional thing. So see, there is a weight. When the weight is not updating, the weight is decaying. You see this case 2, that the weight is falling. You see that?
Yes, sir.
Blue curve that is falling. So there is no weight update here. The VGS is 0. So there's no weight update has been given to it. We're not asking it to update its weight, but the weight is decaying, right? So this has a negative impact, right? You are losing your values. But what we show that despite the fact that we're losing values, at least for simple networks with one hidden layer, the system still works. Makes sense? Now this is early 2021 result. The late 2021 result shows that when you try to do larger networks like convolution network with Spintronic devices, the devices work, the network works because the weight values are retained. But if we try to do more complicated networks for, you know, cipher 10 dataset, right? Have you heard of the cipher 10 dataset or cipher 100 dataset?
Yes.
So if I want to do IDs or MNIS, do I really need a convolution network? Yes or no?
MNIST can work with the fully connected network also.
Exactly. So my point is that if I use a fully connected network with 1 or 2 hidden layers, this transistor synapse will work. Okay. Why? Because it trains very fast. All right. On the other hand, the moment I do convolution network, this system fails. Why? Because the training time is much higher, and by that time the weight values lose. So what I'm trying to say is the result that I showed earlier for spintronic synapses on IDS dataset or MNIS dataset, this can be extrapolated all the way to cipher 10 or cipher 100 for convolution network. That is not the case with these devices. Make sense? Make sense?
Yes, sir. Yes.
Okay. Now, so now that we have done those crossbars that I showed were essentially not very biologically inspired. I mean, the biological inspiration there was that some neurons were connected with some other neurons through synapses. That's it. When it came to information flow, when it came to information update, we were not really using very, very biological inspirations while designing our system. So what is the biological inspiration that has eluded us thus far? That is essentially the spiking behavior, right? So inside the brain, the neurons, when they transmit information, in the form of spikes. Make sense? So if they transmit information in the form of spikes, the power consumption is low because your circuit is not active when there is no spike. Okay, that's why brain consumes a very low amount of power to do a lot of computation tasks. On the other hand, modern computers consume such a huge amount of power to carry out these tasks. Okay, so now what I do show is here, say the now we are trying to design neural networks here. Earlier the neural networks here were just using the crossbar without using spiking. Now you're going to use crossbars along with spiking. Okay, so the basic structure that we're going to follow is this: that you have a bunch of neurons to which your input signals are coming, and based on the strength of the input signals, those input neurons are going to fire. If the signal is strong, the neuron is going to fire more. If the signal is weak, the neuron is going to fire less. And now those input neurons are connected to the output neurons by these different synapses. STDP synapse or spike time dependent plasticity synapse, where based on the relative timing of this firing of these input neurons and the output neurons, these STDP synapses weights will get adjusted. Make sense? Does it make sense? Okay, so now what happens is that we first of all, can we make these new kind of neurons with domain-wide devices? Yes, we can, because what we do with the domain-wide device is this domain-wide device behaves like a leaky integrate fire neuron. So you will not hear about leaky integrate fire neuron or spike type dependent plasticity if you're in a standard ML class, because those ML classes, the algorithms are more interested in getting the job done as opposed to trying to mimic the brain. But if these ML algorithms or the neural network algorithms are done to mimic biological behavior of the brain, then there the neurons or the synapses will follow this kind of property. So in the leaky integrate fire, what happens is that it's a capacitive model where when the current comes in, the voltage across the capacitor goes up as an integral over the current over time. So in the domain wall device, such a thing can be seen because the position of the domain wall is proportional to your voltage. So as in, if the position crosses a certain threshold, your domain wall device will trigger a spike like a neuron does. And the position of the domain wall is proportional integral of the velocity over time, right? Any position is integral of velocity over time, right? And if the velocity is proportional to the current, which is proportional to the input, then the position of the domain wall essentially becomes an integral of the input current over time. And the domain wall device does follow a leaky integrate fire neuron property. And what about synapse? See, an STDP synapse, is there anyone here who has heard about STDP? Spectrum dependent plasticity?
Yes, sir.
Wow, in what context have you heard about it?
Sir, I am working in this area in spiking neural networks. I'm currently working with charge-based leaky integrate and fire neuron. So
where are you working?
Sir, I am a PhD scholar at IIIT Delhi.
Acha, very good, very good.
Yes,
so if you're in STDP synapse, what happens? So based on the new synapse.
So it's based on the spiking behavior of two particular layers of neurons. So right. I have a presynaptic layer and a subsequent layer. So based on the firing, so if my presynaptic layer neuron results in the firing activity of a postsynaptic neuron, so I increase the weight. So the network thinks that probably the presynaptic neuron firing initiated increase led to the firing of a postsynaptic neuron. So I increase the weight. So vice versa, if my postsynaptic neuron fires first and again then my presynaptic neuron fired, so it was probably a misfire. So I decrease the weight.
Exactly.
So it's done locally in the system.
What we do show here is again the Spintronic device, whatever based on the current field, conductance will change. Now this subthreshold transistor circuits that we have designed is essentially doing that phenomena, right? What happens is that the neuron spikes are coming at these gates of these transistors, and based on the intelligent design, we have been able to charge up this capacitor or discharge this capacitor, okay? And how do you get this exponential nature that you have, right? That if the timing difference between the pre-neuron spike and the post-neuron spike is large, your drop is small. And if they're very close, then the drop is, the weight change is large, right? How do you have this exponential nature? So we remember that when the transistors operate in the subthreshold regime, its current is exponentially, like the current is proportional to the exponential of the gate voltage, isn't it? In subthreshold regime?
Yes, sir.
So if I make a capacitor charge or discharge, right, its voltage is changing linearly with time. Okay. And if I apply that voltage at the gate voltage, then the current, what happens to the current? Current will change exponentially with time, isn't it?
Yes, sir. Right, sir.
Right. So that is what you're doing.
So you are essentially operating the transistor in the sub-threshold regime.
Sub-threshold regime, so that your gate voltage is changing linearly with time because you are charging or discharging this capacitor C1 and C2, and then the gate volt essentially that is leading to your increase or decrease of the current as the exponential function of time. Okay, and when the current is flowing through a domain-wide device, the conductance is proportional to the current, so conductance is changing exponential function of time. Make sense?
Makes sense, sir. Right.
So that is how you do it, and because it's non-volatile, once you make the change in weight, it stays there. All right. Now what we do is we use this physics and we have trained it on Fisher-Syrtis dataset, which is simple dataset, and we get very high accuracies. Now, when we want to do it with all transistors, as opposed to using spintronic devices, everything is kind of the same, only that the fact is in transistors is charge based. So if I change the weight by a certain amount, it doesn't stay there, it loses its weight. So when we try to train it on transistor-based synapses, we did show that we did train the network at a full network level and achieved about 60% accuracy. We designed the entire spiking neural network on cadence, and we give the right kind of signals and all, and we trained it up to like 60% accuracy with it. Okay, so now let us move to oscillator-based computing. So before that, maybe I can stop for a couple of minutes and like take more questions. And then we'll finish up with the last two, which are oscillator-based computing and quantum computing. And then we'll be well within time with this stuff.
So suppose you are using, you're classifying for an MNIST data set. So how do you took the input for the, so the input has to be in the form of spikes. So how did you model the input which you are applying to say a spice network? So
okay, so what happens is that's a good question. So what happens is that at the input layer we have put a lot of LIF neurons. All right. Okay. So now the input layer we have put a lot of LIF neurons, and then the input is just the regular input, right? If I have an MNIST image, some of the inputs are proportional to the intensities of the pixels. Okay. All right.
Okay, sir.
So based on the intensity of the pixel, if it's large, your neurons will spike quite a few times. And if the intensity is low, the neurons will not spike much. All right. So that's how we are training it. Okay. Now, some people will say this is not a very good way of training a spiking neural network. Okay. You should ideally work with spiking inputs itself. And there is a dataset called NMNIST, a neuromorphic MNIST, which is a spiking version of MNIST. You know what I'm saying?
Okay.
So
I was not familiar with that.
Yeah, so there are some people who are trying with NMNIST as opposed to pure MNIST.
Okay.
Okay, but we haven't been able to explore that yet.
Okay, sir.
Okay, then any other question?
Also, sir, how? Okay, so the weight update was done by operating the transistor which you used as a synapse, and you operate that synapse in the sub-threshold regime.
Yeah. Now weight update is happening, depends. So there are some transistors which are operating in the sub-threshold regime that generates the right current, and then if I want to use a domain wall synapse, then this right current passes to the heavy metal layer, moves the domain wall, the weight changes. Instead of using this spintronic synapse, if I use a charged transistor, all I need to do is put a capacitor or a transistor 3-terminal device here, and that will be charged up or down by this gate. So the purpose of these other transistors are to operate in the sub-threshold regime and to give the right exponential current that you need.
Also, sir, how compatible are these devices with each other? Say a charge-based MOSFET or and a spintronic-based device.
So spintronic is spintronic devices and charge-based devices. At least maybe not in my lab, it is probably not there very compatible, but in industry it's fairly compatible, because if you look at STTM RAM, spin transfer torque magnetic RAM, that's a commercial product. That essentially has that spintronic device, the magnetic tunnel junction and the transistor built together.
Okay.
I mean, it's a complicated process flow, but it works.
Okay, sir.
But it is not something which you can do today in the lab, within the academic setting that easy. but in the industry it does work. Okay, so one advantage of Spintronics is it's CMOS compatible, as in you can have Spintronic devices with transistors. That's why people are thinking about using STT-MRAM in cache memory. Okay, because cache memory has to be CMOS compatible, right? Because cache memory is on the same chip as the your rest of the circuit, right? On the processor, right? Okay.
Yeah. Okay, sir.
Okay. Now let us go into the oscillator-based computer. So I will start with make it. This is the work I'm actively working on now. So what is an auto oscillator? Let's start with that. It depends on how you want to loosely define how you define these terms. For a long time, I used to mean that if I were what I used to call what is called auto oscillator, often I used to call it oscillator, and what people call damped oscillator, I used to call it a resonator, right? So either way, when you have an what is that called? A differential equation in the second order, right? An RLC circuit is a differential equation in the second order. But is an RLC circuit an oscillator just by itself? Hmm? What is the difference between a resonator and an oscillator? Hello? Hello? What is the difference between an oscillator and a resonator? Who wants to answer?
Sir, oscillator produce periodic signal while resonator only resonate with a certain frequency.
True, but that's
Yes.
more like you are just explained the two words, right? What is input resonator? What is input to a resonator? Is it a DC or is it AC? The output of both are sinusoidal signals, AC. What is input? To a resonator? Is it AC or DC?
It can be AC, like for a particular frequency, it resonates with the tuning frequency.
So if the input is of a particular AC of a particular frequency, the output is also of that frequency or some multiple of it, and it's a response to that input, right? But in case of oscillator, what happens?
We just give a trigger signal, DC trigger signal, and it will go to the some particular.
It just extracts power from the input signal. So it can be DC, and it is giving an oscillation. So, but are these two connected? I mean, given an oscillator, I mean, is there an overlap between oscillator and resonator, or is it the completely different things? Is there a connection? Have you ever thought about it? Like, can you convert a resonator to oscillator, or how do you do that?
Sir, if circuit architecture is different, then we cannot. There is a difference. On a circuit level, it is a different both resonator and oscillator.
No, but if I give you a resonator,
we cannot convert to each
if I give you a resonator, how will you convert it into an oscillator?
Then we have to redesign it. I don't know, but I don't have any idea about this.
Like, for example, if I give an RLC circuit, if I give an RLC circuit, that's a resonator. That's not an oscillator, right? How do you turn it into all these oscillators, like this cold pit oscillator and this oscillator and that oscillator? How do you do that?
Then we have to use
feedback.
Exactly. Feedback.
Yeah, so positive feedback is used, and we apply some noise to initiate.
Yeah, so the noise it will pick up from the environment, right? That you don't have
Right.
to worry. You just have to give a positive feedback. So now in a magnetic system, similar things can happen. So if you have a magnetic field and you start with the magnetic moment, the moment precesses about the magnetic field, right? But then there is damping, gradually it aligns along the magnetic field direction. Okay, so that's what is that then? That's the resonator or that's the oscillator? If you have a DC magnetic field, you give a magnetic moment, it will precess, and gradually it will align along the magnetic field. But if I have to make it continuously oscillate around this magnetic field, I give it an AC magnetic field. Does it make it a resonator or does it make it an oscillator? Hello?
So for being an oscillator, feedback should be present. So if there is
Exactly.
any
So
feedback,
this is an oscillator, this is a resonator. A magnetic moment rotating around a magnetic field. Is that oscillator or is that a resonator? What do you think? Hello? It should be a resonator, right?
A resonator.
Yeah, exactly.
There is no field.
And it's aligning along the magnetic field. And to make it oscillate continuously, you need to supply AC magnetic field outside. So all this MRI, FMR, all this magnetic NMR spectrum, NMR, you know NMR, right? Magnetospectroscopy. NMR, heard of it? Heard of MRI?
Yes, MRI.
So all these things work on the principle of magnetic resonance. Makes sense? Make sense?
yes, yes.
Okay, so now you can give a twist to it and then it becomes an auto oscillator. Okay, so the word resonator oscillator, sometimes some people call resonator damped oscillator and call what I'm calling oscillator as an auto oscillator, and it's something which oscillates on its own. Okay, so it's just a difference in terminology. But either way, so once in this magnetic system, if you have a spin transfer torque, the spin transfer torque provides you. So what essentially is happening is if you have the magnetic field like this, and your moment is gyrating around it, you see this green arrow, it is gyrating around this magnetic field. Now, as it is gyrating, gradually it will start to align along this magnetic field because of this damping torque. Now, what happens with the spin transfer torque, again, because of exchange of spin momentum at the interface, it will work against this damping torque, and it will make the magnet continuously oscillate. And the spin transfer torque is fed by a DC current. Does that now make it an oscillator? So I'm feeding a DC current in the system, no AC magnetic field, but yet the magnet is processing about this exchange, this large DC field in a particular direction. Does it make it an oscillator or does it make it a resonator now? Huh? Did you follow what I say? Yes? The moment was trying to align itself along the field, but I've been able to counter that with an extra torque. And now it is continuously rotating while the input is a DC current. Is that a resonator now or an oscillator? Oscillator, very good. So now, and then the frequency of that oscillator, so here we are showing through micromagnetics that you can essentially apply a DC current and make all these magnetic moments oscillate in unison. That is, they're all, you see all the moments are parallel to each other while it is rotating in a 360-degree circle, right? So, and the frequency of that can be controlled by applying current density. Higher current means it is processing in a larger angles, so it ends up being a lower frequency. Now, it's very interesting property can be seen is sure an auto oscillator, you are applying a DC current and it is oscillating about a certain frequency. Now, if I apply an AC magnetic field or an AC perturbation to that system, what happens to it? Now, this is not just true only for a spintronic system. It can be true for any general oscillator system. If you have an auto oscillator and you apply an give it an AC perturbation of a certain frequency, what happens? What do you think happens? The oscillator is oscillating by itself for a certain frequency, say capital F. Now you apply to it another frequency, say an RF perturbation you give to it of small f. What happens? Do you think?
Interference between different frequencies.
Right. So that's good. So what we typically see is that if this external field, say small f, so external frequency small f is very different from capital F, it fails to interfere. The auto oscillator keeps oscillating at its frequency capital F. Okay. But if this small f is close to capital F, then within a small range, the auto oscillator's frequency changes and it takes the frequency of the applied external field or external perturbation. You get what I'm saying? So you can see in this curve that outside a certain range, the oscillator is just oscillating at its original frequency, which is 6.96. But then within a small range of 0.1 gigahertz or something, the oscillator takes the frequency of this input frequency. Make sense? Does it make sense?
Yes, sir.
Okay. So now we are going to use this physics to show data classification. So why are we talking about this oscillator suddenly so much? So we have this multiple spin oscillators, and to them we apply different RF magnetic fields of different frequencies, and we make these oscillators synchronized to these RF fields. And we plan out these RF field frequencies, the external RF field frequencies, to be proportional to some inputs. Okay, so we take the input. It can be an MNIST image, it can be Fisher sizes, sepal size, petal size, this 4 information, pieces of information. We take that image or take that input vector, and we use some reduction technique, dimension reduction technique, like you know about PCA, NCA, and then there is this TSNE, all that. With this dimension reduction technique, we bring it down to 2 dimensions, right? And we get clusters, nice clusters in 2 dimensions because of this dimension reduction technique. Now, once we have this, these clusters correspond to different values of these frequencies, okay, of RF frequencies. And based on what those values are, different oscillators are going to synchronize to them. And so we look at the synchronization patterns and we see that for a certain cluster, say for example, I take the Fisher series data set. It has 3 classes: Cetrosa, versicolor, virginica, as I was showing before. Now these 3 classes correspond, 3 classes correspond to 3 different clusters. Each cluster will have its own unique combination of what spintronic oscillator is synchronizing to it and what spintronic oscillator is not. And accordingly, I'm going to be able to classify these classes. And we have been able to publish this work also very recently. Okay. So with that, I would, if you have any question at this point with this oscillator synchronization, please let me know. Hello? Nothing? All good? Okay, so I will skip the slides on quantum because it's completely different. I mean, the idea is again to do AI with it or ML with it, but it is in quite a different direction. So, so I would skip this and I would just, I'll stick to mainly spintronics and transistors for AI. And so that's what I've covered. It's important to thank the funding agencies because they make the research possible. So I would thank DST, ACRB, different projects in IIIT Delhi and MHRD, STARS Award, for funding this research. And I would thank IIIT Delhi's organizing team for giving me this opportunity to present my research to you all. So with that, I will end my talk, and maybe we can have 1 or 2 more questions and we can end it up. Sure.
Thank you, Dr. Debanjan. Thank you. Thank you very much for the talk. And I think, yeah, you kept it very interactive. So that was a very good thing. So just wanted to know, what is this STARS award, MHRD STARS?
So this is called Scheme for Technological Advancement and Transfer or something like that on National Science Day in 2019, I think.
So this is like a PhD fellowship for
no. This
student, or it's a research grant for faculty?
An equipment grant.
Okay, equipment. Okay.
So we got a large equipment grant through this.
Okay.
And I think they had only 1 phase, and after this they have stopped it. I think please keep an eye on it because they might open it up for another phase. So.
Okay, because I have not heard it before.
No. This is on National Science Day in 2018 or 19. They inaugurated it. So we got it in the first phase.
Wow.
Then I think they will probably open it up again for other phases. The amount of money they give is pretty large.
Okay, nice. Yeah. Okay, so I'd like to ask participant any question, any queries from your end. Okay, so just wanted to ask a couple of things. So please share the slide with us. So also we have recorded the session.